Good afternoon, everyone. I'm Nhung from Hanoi University of Pharmacy, and today I will present our hierarchical multi-agent reinforcement learning for optimizing CRISPR-based polygenic therapeutic design. As you know, CRISPR is leading technology in precise gene editing by using guide RNA and Cas protein to create double strand break. From that will be gene lock out or using template for gene lock in. However, the off-target effect is the main concern. So recently, advancement like base editing or RAM editing is using for more accurate and effective alternative. CRISPR in vivo CRISPR application require a target and effective delivery system that AVV vector is a preferred delivery system because of the minimal integration to host genome and suitable for a variety of serotype of different cell tropism. This is the reason why CRISPR-Cas9 and AVV are very attractive domain for many scientists. According to WHO, about 1.3 billion people are affected by the vision impairment. So, because the favorable anatomical eye structure and privileged immunogenic characteristic, a lot of CRISPR-Cas9 ABV has been used to correct a large number of mutations related to inherited retinal disorder. However, there are some challenging that we need facing. There are polygenic mutation disease of target effect, limit viral packaging capacity, and immunogenicity. This is a motivation for our research team to develop a method to optimize CRISPR strategy for polygenic disease while balancing edit efficacy, vector capacity, and immunogenicity. This slide about the polygenic scenario that we stimulate on the selected genes is integrated with the IRD disease. They are retinitis pigmentosa and Usher syndrome, and these genes also show the mix of critical retinal function like phototransduction cascades of PDE, 6B, and RHO, the structural integrity of RP1 and USH2A, and the fundamental cellular process of PRPFH. The combination of dominant and recessive inherently very suitable for evaluate the complex gene interaction and reflect the clinical environment. About the computational framework, we used one megabyte toy genes that's suitable for our local workstation. On targets are scored by rule set to range from 0 to 1. The off-target score is off-target score is including 3 component safety score range from 0.1 to 4 and below 2 is accepted therapeutic risk. We also integrate a synergy matrix that quantify the beneficial of co-edit genes and immunogenicity screening for some known motif. To be specified about the synergy matrix, we have a 3 level: the high, the moderate, and low level, and the precise value is present in the table. The CRISPR therapeutic design problem is facing with the challenging how to optimize the guide RNA, how to adapt the clinical feasibility, and how to deal with the clinical constraint. It's a complex multi-dimensional optimization problem. That's just one trend in one favorable effect whole the system. So our solution is develop a hierarchical AI agent that learn to collidate and make optional choice through reinforcement learning. Our architecture includes 3 levels. The first level is design the guide RNA for each gene. The second level is integrate multi-gen strategy that balancing the efficacy, safety, and feasibility. And the last is incorporate the clinical constraint. The information will flow between the level 2 and level 3 from the bottom up and top down. That will finally find the optimal clinical solution. Our training will have a 4 phases. The first phase is optimize the guide RNA design. The second phase is integrate the clinical constraint. The third phase is crucial that the TSA will train in synergy and clinical feasibility based on the feedback of TSA. And the last phase, we will deploy multiple design trials to find the optimal CTA action. We have 3 types of reinforcement learning agent. The GDA to optimize guide RNA with use PPO algorithm. The TSJ, we also use PPO algorithm to evaluate the clinical feasibility, and the CTA, we use deep field network to evaluate the constraint like capacity and immunogenicity. This is our result. We have integrate 4 our 5 genes with selected optimal gene editing mode. The editing mode is based on the type of mutation. RAM editing for PDE6B and RHO for point mutation. Base editing for RP1 is the translation from translocation from C to T, and the lockout for UHS2A, that's the loss of gene in the therapeutic function. Our framework also certified with some clinical constraint about the vector capacity. Our design is 3,900 base pair out of 4,500 base pair of AVV, and the immunogenicity 1 out of 2 epitope, and is in the set. We also have a high synergy utilization. Is the 30 synergy score demonstrate effective gene interaction modeling. In conclusion, we have successfully developed a hierarchical multi-agent reinforcement learning that balancing between editing efficacy, immunogenicity, and capacity. This framework can be applied for any type of polygenic disease and will reduce the time from year to days. We also have some limitation about the computational simplicity, no experimental validation, single disease focus on retinal degeneration and delivery complexity for multi-gene vector. Our future work will focus on validate our framework through experimental design and integrate full genome analysis and state-of-the-art machine learning model, as well as we can explore to other polygenic disease like cancer or neurodegeneration, and also optimize dual AVV system and explore novel delivery platform. And thanks for your listening. And if you want more talk about this research, we can meet at the poster tomorrow.
Yeah, thank you. Yeah, we don't have time questions, so we get cross.